you know, what I want is in the index card itself, I want you to put a picture, right? So not a picture attached to the index card, but on the index card, the picture should be there on the index card. Well, not printed, but you can staple it, you know, stick it with the glue, you know, saliva, whatever, doesn't matter. End of the class. Okay, so finally we can get started. So last time where we left off, we talked about what to do with procedure calling, different things that we need to do in terms of chores, and so essentially what happens on the stack is all kinds of interesting things, right? So if there is a sequence of calls that you make, main calling foo, foo calling bar, bar calling baz. So then what happens is the stack keeps growing, right? And keeps growing and shrinking as you make these procedure calls, nested procedure calls. And as you come back, you're going to pop up the stack, the activation. And so this stuff that is pertaining to a particular procedure call is what is called the activation record, right? And if you look at the contents of the activation record for any particular procedure, there's going to be a whole bunch of stuff that is on the stack. And what are all the things that are saved by the caller? And what is called saved by the callee in this? So is this saved by the caller? The T registers is saved by the caller. Additional parameters, of course, the caller has to place them. And space for the return values, the caller has to do that. And the return address for this guy to know where to go back, right? And so that has got to be saved in here, right? So up to here, this is all stuff by the caller that is being placed on the stack. Everybody with me here? Okay. And now the rest of it is what is going to be done by the callee in terms of the registers that the callee may choose to use, the S registers, it may have to save that. And if it needs local variables, then it has to allocate space for that. So all of this is part of what the callee has to do, right? And now, so if I'm in, let's say, this particular procedure, and those are the contents of the stack, will the, and if I don't make any more procedure calls from here, will the stack grow? Will the stack grow any further? Because let's say that, I've gotten here and Baz is executing the procedure, and now can the stack grow? Nick? Abhishek? Yes? Oh, you said yes to my question, but is yes the answer to my question? You didn't get the question. Oh, okay. So I'm saying that this is the contents of the stack when Baz is executing, right? And Baz is not going to make any more procedure calls. Okay. So given that, will the stack grow any further? Or in other words, will the stack pointer change? And what would be the reason for? Chris? Pardon me? Conditional, like what? How do new local variables? So take C program for instance. How does that happen? Shashank. Well, so then you're making a procedure call. I'm saying that Baz doesn't make any procedure calls, right? So given that Baz is just executing code, Vladimir, right? Yeah. Any reason why it might grow? How? Shane? It's on the stack. It's already there, right? So all of that stuff is on the stack. All I'm saying is, pardon me? New variables now, how do the new variables come about? What happens in a high level language that causes new variables to come about? What's your name? James? Any reason? Joe? Any more growth in the stack? Right. So Joe says there's no more growth in the stack. No, Matt. Okay. So Abhishek, do I start here? Where do I start writing? Okay. So so Baz is here, right? inside of BAS, suppose you have a conditional, right? You have a conditional and then you declare a variable inside this conditional. You can do this, right? So if I do this, all variables that let's say this is x, y, and z. So you have int a, b, and c. I would have declared it up here. So these guys are already on the stack, right? But if this predicate evaluates to true at runtime, then you're going to go ahead and allocate new variables, right? Which means that the stack can grow, right, Joe? Right? So the stack can grow even though you're inside the same procedure and you're not making any more procedure calls. The stack can grow, right? And how does that affect anything? How does that affect anything? Why am I bringing that up, Joe? With respect to, see, remember the addressing mode is base plus offset, right? So, the base register, what is this base register for accessing the local variables? PC? What is your name? What's your name? Charles. So Charles, you said? SP. So PC is good for branches, right? But for accessing variables on the stack, what you need is a stack pointer as the base, right? And so if I have this, local variables declared, all the offsets are going to be with respect to the stack pointer. Okay. But now, if I have inside of this code block, I say that if once I'm going to say x gets a plus b, right? Suppose I say this, the offset that I have to compute here is different, right? Because the stack pointer value has changed, and this is a bit of whose problem is it? I mean, it's still it's all good, right? So I can compile it. I just have to generate a different offset depending on where I am in the program. But whose problem is it? Who's the guy who's going to be really upset that they have to recompute the offset all the time? So Zoeb, right? Compiler writer, right? The compiler writer is going to be saying, "Oh, wait a minute, the offset is changing, and I have to keep computing new offset depending on where I am in the code, right?" And that's the reason why we introduce this concept of a frame pointer. So we introduce a new thing called the frame pointer, and the idea here is, from the point of view of the compiler writer, it'll be really, really convenient if there is a fixed harness on the stack, right, with respect to which all the offsets can be computed. Because we know that during runtime, the stack pointer can change even within the single procedure. But what we want is, in spite of that changing, I want a fixed harness in the stack so that with respect to that, I can compute the offset for the compiler writer, making his job easier. Everybody with me here on that? Right? So that's why here again, this is a convention, right? Some compilers may choose to use a frame pointer because essentially what you're doing is you're taking one of the registers and saying, I'm going to dedicate this for a particular purpose, right? So that's a convention. So some compilers may choose to do that, some compilers may not choose to do that, but if a compiler chooses to do that, then what happens is there is additional work that needs to be done, and this is the same code base that I showed you here. So essentially showing that the offset for A, B, and C are going to be A and B are going to be different here as opposed to the offset over here, right? Because this is outside this code block, and therefore by the time I come back here, I've popped off the local variables I put on the stack, and therefore this offset is going to be different. And therefore, what we're going to do is we're going to introduce a new register called a frame pointer. And I showed you that everything up until this point, right? Everything up until this point is done by the caller, right? This is the caller's portion of the stack. And now what I'm going to do is, as soon as I get into the callee is going to say, well, I'm going to mark where I am on the stack. And from here on, everything is my stuff. And so that's where the frame pointer is going to be harnessed. And so you have a frame pointer value that is coming into you from the previous procedure. And that frame pointer, you're going to put it on the stack. So this is what the callee is doing. So the first thing that the callee does is it says, okay, I'm going to take the current value of the frame pointer and put it into this location of the stack. Okay. So up to here, the stack pointer and the frame pointer are exactly at the same spot, right? The stack hasn't grown yet, right? Now I'm going to start putting other stuff on the stack. I'm going to put any S registers that I might use, I'm going to put it on the stack. Any local variables I'm going to put on the stack, and now the stack pointer is going to keep growing, right? But the frame pointer is stuck here, right? It's always at this point. And so this is a starting point for the activation, the portion of the activation record that belongs to the callee. Everybody with me here? It's a very, very important concept, and I'll test you on it. Okay, so this is where the frame pointer is going to be, and now it doesn't matter, right? Where I access A and B, it doesn't really matter whether I'm accessing it here or accessing it outside of this and so on. It doesn't really matter because the offset is always going to be the same with respect to the frame pointer. Okay, so this is a new concept that I wanted to introduce, which sort of completes all the new concepts that I want to talk about in designing the instruction set, right? So it's actually not an instruction set design issue, but it is again the interaction between hardware and software, how the software is using the facilities provided by the hardware. The hardware is giving you a bunch of registers, and the software is saying, well, I'm going to use some of those registers for dedicating them as parameter passing areas, some of those registers for getting return value, some of those registers for the target of a procedure call, some of those registers for a link register to know where I want to come back. And here is another use of the register saying that, well, I want to use one of those registers as a frame pointer so that I have a fixed harness into the stack. James, is that clear? All right. Okay, so so now we can just talk about the LC2200 instruction set. Very simple. It's got 4 classes of instructions, and this is as powerful. Okay, I mean the number of instructions you've got is 1, 2, 3, 4, 5, 6, 7, 8 instructions, as powerful as whatever processor you have in here, right? In terms of its completeness, you can do anything that you want to do on this machine that you can do on this machine. Maybe a little slow, right? But you can do it, right? So that's the power of instruction set design that says that, well, let's think about what is the minimum set of instructions that I need in order to do everything that I want to do. So you've got add and NAND instruction, and you all have had 2110, right? So what is a universal gate? Universal gate. Have you heard of this? NAND and NOR. Why is it called a universal gate? No, more than that. James. Pardon me? You can make any gate from an AND gate, right? So you can have, if you have an AND gate or an OR gate, that's not powerful enough, right? But an AND is powerful because you can make any logic function with an AND. And that's the same sort of thing with an AND instruction, right? So the reason why you have arithmetic and logic instruction is so that you can do anything that you want in your program, right? And if I have add, that's good, but I don't have a subtract instruction. But if I have a NAND instruction, I can use that to complement bits, and I can implement any logic, logical evaluation that I want for an if then else construct can be implemented using NAND function. And so this makes it a very powerful combination, an add instruction and an AND instruction, in terms of being able to implement any arithmetic or logic function, right? If you want multiplication, you want division, you can implement all of that using these 2 primitive instructions. And then the I-type instructions they're called I-type because they use an immediate operand in the instruction. So if you look at this, the format of this instruction, it's got 3 registers. It's a 3 operand instruction, right? It's a 3 operand instruction, and 2 operands are source operands. Okay, in this case, Z and Y, these are the 2 source operands, and X is the destination operand, and Ron, right? So Ron wanted all the arithmetic and logic instructions to use registers, right? And therefore, we've got 3 operand instruction, 3 register operands. 1 is a destination, and 2 are source registers, right? And in the immediate instruction, what we have is you have only 2 register specifiers, and the third specifier in the instruction format is the offset. Okay, and this is going to be used in several different ways. So if you have oftentimes in programs you have the need for generating constant values, right? So zeros and ones are popular constant, but you may have other constants also that you need to generate in the program, and so having an immediate field in the instruction allows you to do that, and so that's why you have this immediate mode instruction. And so add immediate basically is going to say, well, we'll use x as the destination, and the 2 operands are going to be y and whatever is the offset that is specified in the instruction, right? So that is add immediate. And similarly, load and store, you know that in load and store instruction you have one register as the destination of as the operand, the value that you want to either load or store, and you have to generate an effective address, and the effective address is computed as the contents of a register and the signed offset. And it is a signed offset because that way you're able to generate both positive and negative constants in your program, and whether it is values that you want to generate, or you want to generate an offset with respect to a base register, it's always useful to go up or down in the program, right? And that's what the signed offset gives you. And then the jump instruction, the J-type instruction, there's only one instruction, which is jump and link, and the semantics of this instruction is it's an instruction that allows you to do the procedure calling, right? And therefore, what you need to do is you need to remember where you want to come back, and you need to know where to go to, right? These are the 2 things that you need. And so this X register, Rx, this is going to specify the target of the branch, and Ry is going to specify the link register, and that is where you want to save the contents of PC, right? And that is jump and link register, and branch instruction we've already seen that it's a conditional branch. You take 2 operands and compare them, and if the comparison is true, then you're going to branch. And where do you branch in that case? I mean, I've got only 3 operands here, right? I mean, 2 operands in the offset, and if it's a branch instruction, I'm going to compare these 2 guys, and where do I branch? Pardon me? A label. Now, what do you mean by that in terms of an instruction? Where is the address? So that is where the PC comes in, right? So you mentioned PC as a base register. So this is where we're going to use it for a branch instruction. We're going to say that we're going to branch with respect to the PC. At any point, you're going to say, I want to branch with respect to where I am in the program, and PC is what tells you where you're on the program. And so with respect to that, you can compute an offset, and that offset is given by this guy, right? That is branch instruction. And we don't have a jump instruction. And similarly, we don't have, we said that, you need a jump instruction to return from a procedure, right? But I don't have that. How am I going to return from a procedure? Pardon me? And so it can use a JALR. It's actually saving the current value of the PC. Is that a problem, Joe? Yeah, so you just don't care about the fact that PC is being stored in some register, right? So you can simply use JALR to jump back to where you want as well. So it's doing a little bit more work than what you need for a true jump, but that's okay, right? And we said that when we want to do an unconditional branch also, we'll simulate that by branch on equal, right? Because if I say branch on equal and give 2 registers that are exactly the same, then I'm going to always branch, right? So you can simulate an unconditional branch using this conditional branch instruction, and similarly you can get the effect of jumping anywhere in the program by using JALR, simply ignoring the fact that it is storing the next PC value in some register. Don't worry about that, right? Everybody with me here? So this is a pretty powerful instruction set, and this is what you're going to be implementing in your project, right? Of course, I mentioned that there's a difference between the instruction that I'm showing you here and which is in the book, which is a 32-bit instruction, right? And but on the other hand, for implementation in the project, I'm making life a little simpler for you. by making it a 16-bit instruction, so that you have less wires to lay out and things like that, right? But in terms of power, it's exactly the same because it's got the same number of registers, it's got the same instructions, and so on. The only thing that changes is the number of bits that you've got for an offset. Okay. Any questions so far? Okay. And this is again the set of registers that we got, 16 registers, and how they're used in LC2200. If you use the assembler, this is how it's going to be using it. All of these registers, by convention, we give some specific meaning for all of these registers. And I think you know all this already, so I don't have to belabor this point. And the last thing I want to mention in terms of processor design is we've been primarily focusing on high-level language and saying how the high-level compiling for high-level language influences the instruction set design, and that's largely true. But of course, it's not just the high-level language that influences instruction set design. Applications also play a big part, right? So these days, gaming applications are becoming very important, right? And therefore, if I have an LC2200 as the instruction set, it's going to be excruciatingly slow, right, to do anything interesting on a gaming console. And therefore, there are new instructions that are constantly being added to the instruction set, recognizing that the kinds of things that you may want to do on the processor is slightly different. So you may all heard of MMX instruction. Have you heard of that? So say your name again. Charles. So what is MMX instruction? Well, what's your name? Brian. You haven't heard of it? Let's see. Who have not talked to? You're also a Brian, right? Okay. Let's see. What's your name? Jen, right? Jen. So, you know MMX. What's your name? Chan. Yeah. Don't. Let's see. I don't think I know your name. I think I know your name, but I'm not. Mikey. Any idea? Next to you. What's your name? Ryan. Okay. And your name? Dan. Okay. Anyone? Nate, right? Alazar. Pardon me? Multimedia extension. So what is it used for? Yeah, so basically, in a lot of these pixel level processing, what you're doing is, you're updating, you're doing the same operation, but in a lot of data points, right? So you have, if you're redrawing the screen, then what you're doing is you're computing some value, but the value that you compute is going to be dependent on where you are on the screen. So the operation is the same, but the data is different, right? And so multimedia extension instruction will essentially allow you to do that you can actually specify that the same operation needs to be done on a whole bunch of data. And what that means is that, you don't have to go to the memory for getting the instruction all the time because it's a single instruction, but it's just that the data is going to be different, and that speeds up what you do on the processor, right? So that's an example of how an application may influence the instruction set design. And similarly, the other things that is going to influence the instruction set design, we'll see quite a bit of operating system impact on instruction set design as we go through this course, especially in the context of memory systems and in the context of parallelism and so on. You'll see that there is influence of the operating system on the instruction set design, because all the time what you want to do is you want to make the life of the software writer a little better. And in order to do that, you ask the question, what should I throw in the instruction set architecture that actually makes the life of the software writer a little easier, right? And that's how these things come about. And we will see some of those later on. And then also, so the overarching concern is going to be compiling high-level languages. But a lot of other factors come into play as well. And there will be very interesting instruction set architectures that have died because the company went out, right? Have you all heard of a company called Digital Equipment Corporation? Anyone heard of Digital Equipment Corporation? Nate, do you know anything that they used to do? Okay. See, it's it's a company that did a lot of good stuff, especially in the context of mini processors and instruction set design and so on. And have you anyone heard of alpha processor? See, in the 90s, this used to be pretty good processor, but the company went out and the processor went out as well. But that's an excellent instruction set architecture. But unfortunately, it's not always good engineering or good ideas that make it. Some of the things that influences success or failure is market pressures and so on and so forth, right? And but I just wanted to mention that lots of things that come into play when you think about instruction set architecture design. So I already mentioned the MMX instructions in the context of applications influencing the instruction set design. And in number crunching, if you're doing scientific computations and so on, there are a lot of floating point operations that you have to do, and therefore floating point instructions are very important, and that appears in every architecture that you can think of. Okay, so that's what I wanted to say about instruction set design. Any questions before we move to the next thing, which is going to be processor implementation? Joe. Let me look at it. I don't know what exactly the question says. Maybe at the end of the class, if you want to stop by. Okay. Or Abhishek, do you have a quick answer to that question? The calling convention, Joe's questions. So I talked about the general way things work, and that is specifically with respect to how it happens in the LC 2200. Right? Okay, so now we're going to switch gears and start talking about implementation. So when we talk about implementation of a processor, the first thing is, before we get to implementing, there are two parts to the implementation. One is the data path. The other part is control. So these are the two things that we're going to talk about. But prior to that, I want to give a brief recap of things that you would have learned in 2110, which is the basics of logic design. Right? So that's something that you've learned in 2110, basics of logic design. So we'll cover that part of it. And this is more like I want to find out from you what you know, and so that I can then augment that. A register, everybody knows what a register is, right? So it's a bunch of flip-flops together, and typically a register has inputs which is going to be as big as the number of bits that you have in the register, and the output is of course exactly the same number of bits. And the clock is saying when this input should appear at the output, right? And typically, your clock looks like this, right? So your clock looks like this. It's a continuously free-running clock, and this is what is called the rising edge, right? And this is the falling edge. And have you heard of the term edge-triggered logic? Taylor, what does that mean?
That means that any operations that happen as either edge occurs.
Right, right. So all the transitions in the circuit in a storage element will happen on an edge, and it could be a positive edge-triggered logic or a negative edge-triggered logic. And if it is positive edge-triggered, then all the changes will happen with the rising edge, and if it is negative edge-triggered, it will happen with the falling edge, right? And so typically what happens is, in your circuitry, things are happening. You know what a combinational logic is. What is combinational logic? Brad? What is combinational logic? What's your name? Michael. Alex? Drew? What is combinational logic? Peter? Doesn't have a state. In other words, if you have a bunch of AND gates and OR gates and things like that, then what is happening is using the instantaneous values that you have as inputs, you're computing some output, right? And there is no state, as Peter says, there's no state associated with that. We're just computing something that is based on the current value. That's combinational logic, right? And so you're doing combinational logic all the time. When you're doing arithmetic, for instance, in your processor, then you're taking two values, and then you are adding them together, right? But you're not storing them yet anywhere, right? So you're just computing the result of adding two numbers, and that is combinational, right? And once the combinational function is done, then you can store it in some storage element, okay? And as Taylor said, with an edge-triggered logic, once I've done that computation, I can store that into a storage element so that it is available in the future, right? So from now on, we'll always talk about positive edge triggered. Okay? It can be positive or negative edge triggered, but for the purposes of this discussion, we'll always think of things happening on a positive edge trigger, right? And so the positive edge triggered logic, what happens is, something is being computed here. Maybe there's an ALU sitting here, right? And it is doing some computation here. And as a result of that computation, so let me draw a little picture here. So you have an ALU, and you're getting inputs here. So let's say A and B, and you're computing the output. And this is combinational logic, right? Because it's just taking two values, and then there's a logic circuit that is composed of AND gates and OR gates and NOT gates and so on, that is computing the sum of A plus B. Because sum of A plus B is a combinational logic function, right? So you can express that as a combinational logic function. You can compute that, and then you want to store it in a register. If I want to store it in a register, then I have to clock it, right? So if I clock it, then the value that's being computed here will get into this register. And once it is done, then in the next clock cycle, so suppose I label these edges as 1 and then this as 2, and if this a transition is done at clock cycle 2 at this rising edge, then after this point, right, after this point, the contents, the output that you get out of this is going to be the new value that you just computed, right? Here, the value that you have is going to be the old value. So if you look at the value that is sitting here in this clock cycle, so this is what is called a clock cycle, right? So within a clock cycle, the contents, the output is going to be the old value, what was in the register. And then once this rising edge comes and changes the contents of the register, in the next clock cycle, what you have here is what was computed in the previous clock cycle, right? So this is very important. So one of the common mistakes that all of us make, I mean, I've also made this as when I was learning this for the first time, is when this transition happens between input to output. That is very, very important. So the important thing to remember is that whenever you have a storage element, okay, the contents of the input will not appear on the output until the clock comes in. Okay, so if I have a sequence of things like this, so for instance, if I have a register here, and another register here, and another register here, and if I have a clock driving each one of these guys, right, the same clock, if I have the same clock driving each one of these guys, then input from here will take one clock cycle to get over here, one more clock cycle to get over here, one more clock cycle to get over here. This is very important because sometimes, oftentimes the common mistakes that appear when you try to implement the project is not recognizing when a value appears at the output of a register. Okay, is this idea clear, Joe? Well, we'll come to that. So this is I'm just saying if the clock, if it's a simple register, okay, then you have this this particular function, right? And so let's talk about, is this idea clear? A basic register. Okay, this is a basic register, and and we talked about this already, and now we'll talk about what Joe is saying. So memory may be composed of a bunch of registers like this. That's one possibility. But you can also have memory, as you know about in your box, which is the dynamic random access memory, and that memory is very different, right? It's very different from what I described about a register. And in particular, what happens in a memory is that you give it an address, you give it the data, and you can say whether you want to do a read operation or write operation. So let's say first we want to do a read operation. Then what happens is it takes some amount of time, okay, in order to look up this particular memory location, and of course you're reading, and therefore this doesn't matter, right? And so you're giving an address, and memory is going to look up a particular memory location. Take some time to do that, and there is a particular name for that. Anyone know what that name is? The access time. I just said that. The access time, right? So it is the memory access time that is the amount of time the memory element is going to take from the time you specify an address till the point that it's going to say here is the data that you're looking for. Okay, and that access time, what does it depend on? Any idea? What does it depend on? It's a size, right? So it's a the bigger the memory, the more time it's going to take in order to decode what the address bits are, and then look up that particular memory location and pull it out, right? And you will see if you look at the spec sheets of memory, it will say it's a 30 nanosecond memory or a 50 nanosecond memory and so on. What that means is that that's the amount of time from the time that you specify an address to the point a particular memory location is pulled out and it is available at the data outline. Is that idea clear? So that is the access. That's how a memory works for reading. And as Joe pointed out, the other operation that you might want to do is writing into the memory. Okay, if you want to do write into the memory, then you can simply, if I have a single control line, and if I say that if the control line is not asserted, meaning that it's normally containing a 0 on that line, it's just going to read it, right? But if I enable that write line, okay, if I enable that write line, what the memory is going to do is it's going to take this address, it's going to take this data, and put this data into exactly the same into that particular memory location that this address is pointing to. Okay, and so here you see that there is no clock involved, right? It is purely, and the way it works is very different from a normal register, in the sense that the way the bits are stored inside a DRAM, later on we'll see when we talk about memory systems, is that it may use a capacitance to store the data inside the memory cell. Okay, and that's the reason that there is no clock involved here. It is simply storing, the value as a storage on a capacitance. Joe?
Yeah, how do you know when it writes?
So this is where the spec sheets come in, right? The spec says that it takes so much time. So I said there's a capacitance that is being stored, right? So the electrical engineer is going to tell you that this is the amount of time it's going to take, and therefore that decides what the access time is. So as a designer, as an architect implementing, I'm going to look at the spec sheet and say, oh, this is going to take 50 nanoseconds to access memory, and it may also have another thing which is called a cycle time. And cycle time is saying, if I've given a memory operation, how long should I wait before I give it another memory operation, right? And that goes back to the question that Joe raised, which is how much time is it going to take for that, if I do a write operation, for that to complete, so that I can give it a new operation. So that's what I'm going to use in designing implementing the processor. Okay, so that's the memory element, and so now what we will do is we will look at something very, very simple. In the LC2200 we have an add instruction, and so let's think about what exactly happens, right? So if I have an add instruction, and the add instruction is going to say 3 registers, right? It's going to say the semantics of this instruction is that the contents of our y and our z are going to be added and put into a third register Rx. So this is the semantics of add instruction, and you know that the things that come into play in implementing this instruction is a program counter, because the program counter is pointing to this add instruction at this point of time, right? And therefore what you need to do is you need to go to memory in order to get that instruction. So from the program counter, you want to give the contents of the program counter to the memory, okay? And if you give it to the memory and you specify that it is a read operation, then after some amount of time, you're going to get the instruction, right, out of the memory. So that's going to come out here. And once we have that, then what we're going to do is we're going to put it into a register, okay? And we'll call this register an instruction register. Okay? And so going back to what Joe said, I know from the spec sheet how long the memory is going to take, right? And therefore, what I'm going to do is in designing this clock, if I give the address at this point, I'm going to wait for a certain amount of time, right? And the amount of time that I'm going to wait is going to be decided by the spec sheet, saying that, well, the memory cycle time is such and so, 50 nanoseconds or 70 nanoseconds. I'm going to wait for that, right? And after that, I can clock this register, okay? And then I've got the instruction into this instruction register. And once I have that, then what I want to do is I want to give it to a register file. So we talked about a single register here, okay? And if I basically connect a whole bunch of registers together like this, so I have a whole bunch of registers. So this is register 1, register 2, etc., register 15. Remember that, so let's call it register 0, 1, 2, etc., 15. So remember that we have 16 registers in the instruction set architecture of LC2200, right? And therefore, we have these 16 registers, and so if I have this is what is called a register file, right? A bunch of registers that I've got together, and the instruction register, if you remember, the instruction format is going to tell you if this is the mnemonic for the instruction, but what you really get is a bunch of bits from memory, right? So that's got the opcode, it's got the RX specifier, RY specifier, and RZ specifier, right? So these are the contents of the instruction register. So if you look at the contents of the instruction register, then it's going to look like this. So it's got all these things. And so what I can do is I can send these two specifiers. So how big are these specifiers here? RX, this specifier, and this specifier, and this specifier. How big are these? 4 bits each, right? Because we've got a register file that is 16, and therefore in order to address any particular register uniquely, I need 4 bits. So each one of these is going to be a 4-bit field in the instruction format. And so what I'm going to do is I'm going to give RY and RZ. I was trying to write with this. It doesn't work, right? So I'm going to give this and this to the register file, and that is what is being shown over here, right? So this single line is actually saying that take the address specifiers in the instruction register and give it to the register file, and the register file is going to then spit out 2 values, right? And it is going to spit out the value corresponding to whatever happened to be this RY. Maybe it is R2, maybe it is R5. It doesn't really matter, right? So something that is specified in the instruction register, contents of the address specifiers are being given to the register file, and it's going to pull out those corresponding registers out of the register file. Everybody with me here so far? Any questions? Am I going too fast? Okay, good. So so that's what we've got here. And now we're going to do the arithmetic operations. This is the add operation, right? I'm going to do the add operation. And is this combinational? I mean, when will the output of this come over here? When will the result of this ALU be available? Taylor? Immediately? Well, it takes some time, right? There's a combination logic, and it's going to take some time to compute, right? And so it takes some amount of time, and that depends on the propagation. These are called propagation delays. We said access time for memory, and similarly for combination logic, you have propagation delay, right? If you give inputs to an AND gate, after some propagation delay, the output is going to be available. and if I have a whole bunch of those gates together, then you're going to string those things together, and that is the propagation delay. And after that, this output is going to be available, and you can take this output and then give it back to the register file. And in the instruction register, we've got one more specifier, and that is the the destination specifier. So I give this as the register specifier, and as Joe pointed out, I also have to tell this guy that you now write to it, right? You do write enable so that it is going to use this and the input that's coming in from here, and then put that content of the result of the ALU computation into the particular register that is named by Rx. This is essentially what happens in an add instruction. If you want to implement add instruction, this is what you have to do, right? Everybody with me here? Okay. So I've functionally told you what needs to be done. Can it all be done in one clock cycle, Dan? Can it be all done in one clock cycle? It can be. Of all the way from here to here. Which one? You tell me straight from the beginning, right? So tell me from here, how much clock cycle is it going to take for me to get this into, give to memory and then get the result into IR? How many clock cycles? One clock cycle, right? So because all that it needs is the access time for the memory, right? So given the access time for the memory, then if I give the address in one clock cycle, I can get the contents of this into the IR, right? Then when is this going to be done? So let's see. So in let's see here. So clock cycle 1, what we've done is PC into memory into IR, right? So we've done this. And can we do anything more than this? We cannot, right? Because remember that the output, you hit a wall. Whenever you get a storage device, you hit a wall. The output of that storage device is available only after the next clock cycle. And therefore, we've got this into this instruction register. So in clock cycle 1, this output is meaningless, right? Because we don't have that yet, and therefore we have to wait for the next clock cycle. So the next clock cycle, I can give this, and now what I want to do is I want to basically do IR is going to give it to the register file is going to spit out the contents of the registers, do the ALU operation, and I'm going to store the result back into the register file. Can this all be done in one clock cycle? Nick doesn't think it can be. So what's your name? Jonathan. Can it be done in one clock cycle? More than one. Tim. More than one? What's your name? Michael? More than one. Anyone think that it can be done in one clock cycle? Abhishek thinks it can be done in one clock cycle. Why do you think that? Just like that, just for the heck of it. Joe? Yeah. Well, so okay, so I'm going to do this. I'm going to say that that I can actually specify. So that's a good point. I didn't fully specify the problem. So I'm going to say that into the register file, I haven't shown the details yet, but I'm going to say into the register file, I have three things coming in, right? Three address specifiers coming in. And this is, I'll call this the RY address specifier, RZ address specifier, RX specifier, okay? And I'm going to say that this is the data in. And I'm also going to say that, the circuitry here can actually read multiple registers. I'm going to get the contents of RY and the contents of RZ. Okay? And I also have something else here, which is write enable. And what write enable says is that if you have write enable, the contents of this is going to be used as what needs to be put into the specifier that is coming over here. Okay? And I'm also going to have a clock because it's a register, right? I'm going to have a clock. Okay. So given this specification, can I do it in one clock cycle, Nick? Still Nick thinks it is 2 clock cycles. Taylor? Uh-huh.
So after you get the instructions out of the IR, all you have to do is, since the values are already there, you don't need to wait for the next clock cycle.
That's
for the
right.
values to refresh.
Right. So the contents of Rx and Ry is already frozen in here, right? Sorry, Ry and Rz, they're already frozen in here. Those are the values that we want to pull out, right? Was written in some previous clock cycle, right? And therefore, the contents of the registers that correspond to Ry and Rz, it's combinational to pull it out, right? Even though it's a storage device, I'm just giving it the address, and I'm going to read the contents of that, right? And that can happen in the same clock cycle. Agreed with that, right? And I can do it because, as Joe pointed out the right thing, and that is I have multiple address specifiers, and that's the reason that I'm able to do this, right? So I can pull out two of these values at the same time, and this is what is called a dual ported register file, meaning there are two ports for specifying the address and pulling out data bits. So I can pull out the data bits corresponding to Ry, and the data bits corresponding to Rz out of this, because those are values that have been written previously. It's available inside the register file. I can pull them all out. And so in the same clock cycle, I have gotten the register values out, right? And can I do this in the same clock cycle? I can still do this, right? It's combinational. It just tacks on more time, right? So it took some time for me to pull the registers out of the register file. It's going to take some more time to do this ALU operation. And once I'm done with that, I come over here. Can I write it in the same clock cycle? No? This is the beauty of edge trigger logic, right? This is the beauty of edge trigger logic, that in the same clock cycle, you can actually write it, okay? And therefore, what you can do is, now what we've done is, during this portion of the clock, I pulled out the register bits, done the ALU operation, and the result is already here at the input to the register, okay? Then the clock comes in, the rising edge of the clock comes in. I can put the value into the register file. And it doesn't matter whether the register that you're specifying is exactly the same thing, or in other words, for instance, this could be saying, this could in fact be R1, and this could in fact be R2, and this could in fact be R1. It doesn't really matter. Okay, so you're pulling the old value of R1 and the old value of R2, creating a new value out of the ALU, and you want to write it back into the same register R1. And this is possible with edge triggered logic. Okay, or in other words, this entire stuff that I'm showing you here, from the time that the instruction register contains this instruction to the time that you actually write the result of that ALU operation back into the register file, all of that can be done in one clock cycle. Matt. It is always with the rising edge, right? So in this clock edge, so this is where the control inputs come in, right? So we're going to see that. In this clock cycle, I'm having write enable on, okay? In the next clock cycle, I may turn it off, okay? But in this clock cycle, if what I wanted to do is take Ry and Rz, get the contents out of the register file and write it into Rx, then I want to keep this write enable on, right? The next clock cycle, if I don't want that, I'll turn it off, okay? But the important point I want you to get is that this, even though this seems like a lot of action, right? But all of these are combinational, and therefore you can do that. And the only thing that is involving a storage is writing it back into the register file, and that can be done at the end of the clock cycle. So Nick, are you convinced that it's not possible? What is it that made you think that several of you thought it's going to take multiple clock cycles, right? So let me get why you thought. Okay. So it is because I didn't show you that your register file contains multiple ports, right? That's the reason that you thought that. Now, Ron, why did you think? Same reason, right? So if it is multi-ported, I mean, any other reason that you thought that it cannot be done? I mean, one of the things that you may have thought is that you cannot write to the register file in the same clock cycle as reading the register file, right? That's one. That's it's an obvious confusion that one can have, and that's the beauty of edge-triggered logic. That with edge-triggered logic, you can actually do writing and reading of a register in the same clock cycle, and it can be exactly the same register as well, Joe.
So during the same clock cycle when all this is happening, can you also increment the PC and get the next value out of the PC
Sure.
during the same step?
Yeah, absolutely. See, this is completely independent. This part of it is completely independent. See, the minute you put a storage device, you're isolating action over here from action over here, right? So this action is completely independent of action that is happening in this part of the circuitry, right? And that's the beauty of putting storage elements. When you put storage elements, then you're isolating, the circuitry from one to the other. Okay, very good question. So any other point? So maybe I should stop here, and we'll continue on Thursday. But essentially, what I want you to do is I've given you the sort of a background on logic design. Please review the topic, okay, of logic design, so that we can start getting into Datapath Design for LC2200 and talking about the sequences that you have to write. Okay. I had a PRS prepared today, but all of that is a wash. I couldn't do it today.